Okay, two different questions here. So first of all, for the intervals, completeness, and so on. In fact, it matters a lot how the network is written. Actually, I do have. Okay, if you bear with me, I do have an example. If you bear with me 1 second, I should have put it on slide, but this is. Okay, you cannot see me. 1 second, I'm trying to make it live. Okay, so I don't know if you can see it, but basically, let's say you have this network here and this network here, and you're trying to compute the ranges for y, and these two networks are basically computing the same function, but they're written in a slightly different way. So especially here and here, that's what the difference is. Now, if you do interval abstraction, here you're going to get bounds that are not precise, and here you're going to get bounds that are precise. Just because the way the program is written makes it so the interval abstraction doesn't cancel out like that. So if you want something that is complete with intervals, you need to do this input refinement asymptotically, then you get something complete, like in the rel-val kind of abstraction. This is, yeah. You can do it with symbolic, you can do it with intervals. This is, it's okay. Eventually, you get to something where you can prove everything, but eventually it means you may not do it. It may take, I don't know, a week or a month or something, depending on how large the model is. For deep poly, the problem is that you have, sorry, I don't know why I closed the presentation. I didn't want to do that. For deep poly, let me go back to deep poly. Okay. Okay. For deep poly, the problem is that you have this choice here, and if you, and depending on, and the choice depends really on the range that you have in input. So the ranges that you have here before the redo, this will dictate what abstraction you get. And what abstraction you get will have an impact on how precise you are later on. So just the fact of having this choice, whatever fluctuation you get here will make you possibly get the wrong choice here. And maybe it's an indication that this heuristic of how to pick one abstraction and the other is not the best one, but we don't have any idea on how to pick the best one.
Maybe I'm just not up to speed on what people are doing in neural networks these days, but are all of these are assuming that you're using the ReLU as the activation function?
Yeah.
Do these also work for other activation functions?
Yeah. So these are, I mean, I present this one because it's simpler to get the idea. But in fact, this kind of linear approximation with the lower and upper bounds, it works also for other activations. You can do the similar kind of ideas for other ones. And that's what the alphabet and count people are doing. They have this linear, symbolic linear upper bounds, lower and upper bounds, and they use that. There's something, yeah?
So it seems counterintuitive to me that abstract interpretation will work for neural nets. So here's my question. Whenever you classify an image using neural nets, it will give you a probability, right? Like with 95% probability, it's a dog. So if the program itself is not sure of the output, how is the abstract domain, which is like an overall approximation of the program states, is sure that, yeah, it's true. With this intuition, I feel like the two intervals should always be overlapping.
So, okay. I think I see what you mean, I think. So, in fact, we don't mean, okay, what you get with the, okay, no, let me go back 1 second. No, I went too far, sorry. 1 second. I think maybe what you're questioning is this.
So this is a simple example, but like in practice, we usually not get like exact classifications, and we get like with this probability.
I mean, here you also have some probabilities, right? You have whatever. We're not questioning the choice between the probabilities, right? We're just saying, okay, whatever the output is, so you could actually map this into your abstraction if you want. You could, okay, your output here, what I'm saying, as a simple case, I'm saying, okay, if this input is larger than the other one, then this is the class that we pick. There could be that we want an actual distance between the classes before we make a choice or something like this. This can all be captured by your abstraction, right? It's in practice, it's true that most of the time your abstraction will be not precise enough to actually decide this. Even because okay, with your interval ranges, let's say, you get an over approximation of the range of your output, the range of your probability space, or whatever. And so you map it back to a set of possible probabilities, and you see if this is larger than the other one. So you can work with numbers, you don't need to reason about probabilities. But in practice, it could be that you have overlaps between intervals, and that's where you have to do all these refinement operations, optimizations, and so on, to make it work in practice. And it doesn't work in practice for very large models either. So we can do simple properties like this stability prediction. Local stability prediction works for large models. They have done in the VNN comp, they can do also, I've seen papers where they also handle some form of transformers, right? But if you consider, ChatGPT or LLMs, so this is out of scope. There's no way you cannot handle any of it.
Yeah, I think that's right.
Yeah. Yeah, sorry, yeah.
I have one more question about the polyhedra that you get with the ReLU.
Yeah.
I was confused at why it's so different between the interval as its center to the right of the zero, or the interval as its center to the right of the zero.
Oh, I mean, this is an heuristic that the authors of this abstraction picked. So they said if it's center, we do this abstraction. If it's not center, we do this other one. It's supposed to minimize the orange part. So let me see.
Because with the other polyhedra abstractions, I didn't understand what they meant and where they were coming from, but this one I'm having trouble understanding what it means or where it comes
So okay, so this red part here is the best complex approximation of the value. So x is the input, value x is the output, and the best. So the function itself does this, and so the triangle is the best complex approximation of it. Now, when you approximate with just one lower and upper bound, you just have to pick two of the constraints, of the three constraints of this triangle. So if you pick this one and this one, you are adding this orange part. If you pick this one and this one, you're adding this orange part. And the heuristic is supposed to make you choose the abstraction where the orange part is smaller. So it turns out that if they're sort of balanced, symmetric with respect to zero, this part is smaller than this down part here, and otherwise this one is smaller.
So the range of real possibilities is the red
Yeah,
triangle?
yeah.
Oh.
Yeah, and then all the orange part is stuff that you cannot actually have in practice. I think we are. Oh yeah, sorry. Yeah.
When you're taking the two polyhedra, you said you use a convex hull.
Yeah.
Is that I come from polyhedral compilation, and when you have to do exactly, oftentimes you'll use two disjoint convex polyhedra to represent that. Is that something you've used, or?
No, say that again.
So rather than taking the convex hull,
Yeah.
like two polyhedra, when you join them, instead you could take the disjoint using
Yes.
polyhedra.
Yeah. So okay, thank you. Yes, it's possible, but it's very expensive because actually we will see it. Well, we'll see if we have time to see it. But you can actually do analysis with disjoint polyhedra. It will be more precise. But also very expensive because then you have to do the splitting a lot. So there's a lot of joints that happen in your analysis. Imagine when you have loops, and you're gonna have to do a lot of union, and you get a lot of polyhedra, and you can get actually out of hand very quickly. So it does, in practice, it's better to do the convex side. And then, I mean, in practice, for real static analyzers, they don't, like in the Astray static analyzer for, that they did for Airbus, for instance, they never used polygon because they were just too expensive. The convex calibration was too expensive, for instance. So in practice, they don't use polygon, they use other specific abstractions to, because it works better, it's precise enough, but also scalable. There is a bit of a trade-off, basically, where you pick the abstraction. Okay, good. Okay, thank you.